All right, the next topic that we have in the notes is vector line integrals. So if we go back really quickly here and take a look at this, this would be our definition 2 right here of a vector line integral. Um, we're going to take a look at something separately and then we'll come back to this, but this is the next topic here. How to compute them and what they're defined to be. So if we take a look back over here, this is a document that I wrote up about how to get some intuition behind vector line integrals and what they mean. They can be a little mysterious, I think. So here's my take on it. So essentially what we have is, let's say we have a two-dimensional vector field. So right here. So think of some vector field, capital F, which is defined on the real numbers. The real number plane. All right. Now, quick things to point out here. All these vectors, I made them have the same length visually, but that's just to make the graph more readable. Really, the length of the vectors can be found by looking at and matching the colors. So, all right, so now that we've got a vector field in 2 dimensions, let's imagine that we have a path. And we're going to call this path C. So this path might be difficult to see, but there are arrows here, here, and here, which tell us that this is being traced or traversed in that order. So if you can imagine, you're starting here, and then you're going to walk in this direction and end here. So imagine this is a path upon which someone is walking or riding their bike, something like that. So a vector line integral takes a vector field together with a path and performs an operation. So what I've done in this image is we've taken the above image on the right, this one right here. We're going to take this one, but instead of including all these arrows that aren't on the path, we're only going to look at the actual vector arrows that live on this path. In other words, all the vectors that begin on that path, which brings us right to here. So, same color bar, same length, just a bigger image and less crowded. So we see all the vector arrows here. Again, we still have these little directional or orientation arrows that show us the orientation that the curve is being traced. So what's going to come, what's important here is that a vector line integral, its definition, which is set in the very next page, is this. So specifically, f.dr, the vector line integral, is defined to be the scalar line integral of this. So I do a little work here in the first paragraph showing that when you have, as a quick recap, capital T is the unit tangent vector. So let's go ahead and say that, suppose C is parameterized by some r of t for t in some range of numbers. Okay, then capital T is the unit tangent vector. So this is the derivative of r prime, divided by its own length. So that's capital T. So what we're actually integrating here is f dot capital T. Well, we know that a dot product between two vectors can be written as the product of their lengths times the cosine of the angle between them. And because capital T is a unit vector, we ultimately just get the length of f times the cosine of theta. So what seems to really matter here is that we're adding up a bunch of these little lengths, it seems, or something proportional to that at least. So the length of the vector times the cosine of theta. Okay, where theta is the angle between f and t. So down here, I've essentially kept the original vectors that we had right here, each of these. But in addition to that, I began drawing the tangent vectors. So your line of sight as you move on the curve here. What's your line of sight? So if we do that, that's what these red vectors are. So down here, the red vectors actually represent the tangent vectors. So we can actually take a look at what theta is. So theta is the angular measurement between 0 and pi for all of these. So here we have acute, 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 all of these are acute, until right around here where we get an obtuse angle. Obtuse. This looks pretty close to orthogonal. We could practically say that's orthogonal. And then we're back to acute. So this one was obtuse right here. This one was acute. So somewhere in the middle, there has to be an orthogonal vector. So these are all acute until we get to down here, somewhere in there. So essentially, at every step of the way, what we're doing is we are calculating this quantity, length of f times the cosine of theta. So you can see down here, I've changed this color bar to no longer represent the length of the vectors, but rather what is the value of the cosine of theta, where theta is found for here. So you can see that these vectors here, we have these shades of colors, so that means we're something on this end. This end. So positive numbers for everything in here, positive. And our orthogonal one that's not graphed, but we know has to exist because if this is acute and this is obtuse, intermediate value theorem, since vectors are going to, and a vector field are going to vary continuously, there needs to be an orthogonal one in there someplace. So obtuse vectors right in here, these values are like purple, they're down here in the negative half. So essentially, the value of this depends on what the angle is. So this is positive if theta is acute. It is negative if theta is obtuse, and it's 0 if theta equals pi over 2, if it is a right angle. So I've got an analogy here, but essentially the way I think about this is, imagine you're riding your bike through town along some path. At every single moment of your journey, you are biking in a particular direction. In other words, you have some sort of velocity vector. Maybe your bike's pointing north. Maybe you're now traveling northeast. But whatever it is, at every single moment in time, it seems obvious, but it's important to state that you have a well-defined direction and a velocity. Likewise, at every moment in time, at every position on your path that you're taking on your bike, the wind has some sort of speed or strength, and it's going to blow in a specific direction. So at some times during your path, maybe the wind is blowing, maybe not exactly in the same direction that you're biking, but more or less it's blowing you forward. So examples of this would be any of the vectors along here. Think of these red vectors as your position on a bike. So here we'd be going around a turn. And think of these vectors as the velocity vector of the wind. So it's true that none of these vectors in this region right here, they're not the same vector. They're not pointing exactly in the same direction. But more or less, this wind will positively contribute to your velocity. It will change your direction a little bit, but it's not going to slow you down. It will not slow you down. Right here, this looks like the wind and your position are exactly in the same direction. So the angle appears to be 0 there. In which case, in which case, your velocities will add together very nicely. Of course, down here, when we get to the obtuse angle, the wind is now suddenly blowing in the opposite direction of you. Not the complete opposite direction. The angle is not 180 degrees or pi radians. It's slightly short of that. But regardless, your velocity will decrease here. So it seems like if theta is less than pi over 2, then that means in some sense that the vector field and you on your bike, they're pointing more in the same direction than they are pointing in opposite directions, if that makes sense. So here, there's an additive effect. It's sort of in the same, not exactly the same direction, but you're more in the same direction than you are not in the same direction. Then, right in this area here, you go from an acute to an obtuse angle, so at that moment, the wind is hitting you perpendicularly. So the wind, if you're traveling in some direction and the wind comes in perpendicularly, that wind is not going to affect your velocity in this direction. It's not going to add, and it's not going to subtract in that direction. So there's no effect, and that's why we get 0 here. Once we move into obtuse, it's like you're actively going against the wind because it's blowing against you. In which case, there's going to be this negative effect on your velocity. Your velocity is going to decrease. So the way I think about vector line integrals is by comparing it to the wind. And how does that add or subtract? How do those things add together in a constructive way, or how do they add together in a destructive way?